Good evening, and welcome back to Boring Science for Sleep, the place where quiet stories of the universe help your mind slow down and gently drift toward rest. Tonight, we are going to take a journey far beyond the present age of the cosmos. Not just millions of years into the future, not even billions. Instead, we will imagine a universe that exists trillions upon trillions of years from now. A time so distant that almost everything we recognize in the night sky today will have changed. The bright constellations above Earth will no longer look the same. Many of the stars we see tonight will have already finished their lives. Some will have exploded as supernovae. Others will have quietly faded away. But among those future remnants of stars, there will exist something particularly mysterious. Something that, strangely enough, does not yet exist anywhere in the universe today. Before we continue, I always enjoy hearing from listeners around the world. So if you feel like sharing, leave a comment telling us where you're watching from and what time it is there right now. Some of you might be listening late at night, already wrapped in blankets as the world outside grows quiet. Others might be listening during a peaceful afternoon or while resting after a long day. Wherever you are, I'm glad you're here. Now let's begin tonight's calm exploration of the distant future of the cosmos. To understand the strange objects we'll be discussing tonight, we first need to think about how stars end their lives. Most stars in the universe will not explode dramatically. They will not become neutron stars or black holes. Instead, stars like our sun will follow a quieter path. After billions of years of shining steadily, a star eventually runs out of nuclear fuel in its core. The delicate balance between gravity pulling inward and fusion pushing outward slowly begins to change. The star swells into a red giant. Its outer layers drift away into space, and at the center, a small, dense remnant remains. This remnant is called a white dwarf. A white dwarf is incredibly dense, roughly the size of Earth, yet containing nearly the mass of the Sunday. But unlike ordinary stars, white dwarfs no longer produce energy through nuclear fusion. They simply glow with leftover heat, like a piece of metal slowly cooling after being removed from a furnace. Over time, that heat fades, very slowly, so slowly that the process takes trillions of years. Eventually, far in the future of the universe, the last remaining heat of a white dwarf will finally disappear. The object will become cold, dark, invisible. When that happens, the star will have reached its final stage. It will become something known as a black dwarf, a small, silent remnant drifting through space, no longer glowing, no longer radiating heat, just a quiet piece of cosmic history. But here is the remarkable part. According to everything we know about astrophysics, the universe is not yet old enough for a single black dwarf to exist. Not one. The oldest white dwarfs we know are still warm enough to glow faintly. They have not had enough time to cool completely. Black dwarfs belong to a universe far beyond our present era. A universe so old that even the faintest embers of stars have gone cold. Tonight, we will explore that distant future together. We will imagine the slow fading of white dwarfs, the quiet transformation into black dwarfs, and the long era when the last lights of the cosmos finally dim. So settle in, take a slow breath, and allow your thoughts to wander gently into the far future of the universe. A future where the stars themselves slowly fall asleep, and where the quiet remnants of ancient suns drift silently through the darkness of space. Before a star can ever become a black dwarf, it must first live a very long life. Most stars in the universe begin their story in quiet clouds of gas drifting through space. These clouds, made mostly of hydrogen, slowly collapse under gravity. As the gas falls inward, it becomes hotter and denser. Eventually, the pressure in the center becomes so intense that hydrogen atoms begin to fuse together. A star is born. For billions of years, the star shines steadily. Deep inside its core, hydrogen atoms combine to form helium. This process releases enormous amounts of energy. That energy pushes outward. Gravity pulls inward. And for most of the star's life, those two forces remain in perfect balance. This balance is what allows stars like our Sun to shine peacefully for such long periods of time. Our own Sun is currently in this stable stage of life. Astronomers call it the main sequence. During this stage, the Sun steadily converts hydrogen into helium inside its core. Every second, millions of tons of matter are transformed into energy. This energy travels outward from the core, eventually reaching the surface where it radiates into space as sunlight. The light and warmth from the Sun sustain life on Earth. But even though the Sun appears steady and eternal in our daily lives, it too is slowly changing. Because every second, a small amount of its nuclear fuel is being used up. Fortunately, stars are very efficient engines. The Sun has already been shining for about 4.6 billion years, and it still has roughly another 5 billion years before its fuel begins to run low. But eventually, even a star as steady as the Sun will reach a turning point. Deep inside its core, most of the hydrogen will have already been converted into helium. When this happens, fusion in the core slows down. Without enough fusion energy pushing outward, gravity begins to compress the core once again. The core shrinks, and as it compresses, it heats up. Meanwhile, the outer layers of the star respond in a very different way. Instead of shrinking, the outer layers begin to expand. The star grows larger and larger. Over time, it swells to hundreds of times its original size. At this stage, the star becomes something known as a red giant. Its surface temperature becomes cooler, giving it a reddish glow. But its enormous size makes it much brighter than before. If our Sun were to become a red giant today, its outer atmosphere might extend beyond the orbit of Mercury and possibly even reach the orbit of Earth. For a time, the star becomes a giant glowing sphere filling a large part of the inner solar system. Yet even during this dramatic transformation, the real changes are happening deep inside the core. As the core continues to contract, temperatures rise once again. Eventually, the heat becomes great enough to ignite a new stage of fusion. Helium atoms begin to fuse together. This process creates heavier elements, such as carbon and oxygen. For a while, the star finds a new balance. Helium fusion provides energy. Gravity is once again held in check. But this phase does not last nearly as long as the earlier hydrogen burning stage. Helium fuel is consumed more quickly, and eventually that fuel also begins to run out. At this point, the star enters the final stage of its life. Unlike massive stars, which may explode violently as supernovae, stars like our Sun end their lives much more quietly. The outer layers of the red giant begin to drift away into space. Slowly, gently, the star sheds its atmosphere. These expanding clouds of gas form beautiful glowing shells known as planetary nebulae. Despite the name, planetary nebulae have nothing to do with planets. The term simply comes from early astronomers who thought these glowing clouds resembled the disks of distant planets when viewed through small telescopes. In reality, they are the last breaths of a dying star. The gas expands outward, forming delicate patterns of glowing light across space. Some appear like cosmic flowers. Others resemble ghostly rings or glowing bubbles drifting through the darkness. As the outer layers drift away, the core of the star remains behind. What was once the center of a giant star is now exposed. This remaining core is extremely hot and incredibly dense. Yet it is also very small, roughly the size of Earth. This compact remnant is called a white dwarf. White dwarfs no longer generate energy through fusion. Instead, they shine because they are still extremely hot from the earlier stages of the star's life. They glow faintly, like a piece of metal slowly cooling after being removed from a fire. Over time, they will cool more and more. But that cooling process takes a very long time, longer than the current age of the universe. In fact, every white dwarf that exists today is still glowing. Even the oldest ones have not yet cooled completely. They are still slowly releasing the heat stored during their formation. This quiet stage of stellar evolution is the beginning of a much longer journey. Because a white dwarf is not the final step in the life of a star like the Sunday, it is only the beginning of a slow transformation that will take trillions of years to complete. Over unimaginable spans of time, the white dwarf will continue to cool. Its glow will grow dimmer. Its temperature will slowly drop. And eventually, far in the distant future, it will become something darker, something colder, something that no longer shines at all. A black dwarf. But that transformation belongs to a time far beyond the present universe. For now, the stars we see tonight are still in earlier chapters of their lives. Some are young, some are middle-aged like our Sunday, others have already become white dwarfs, yet none have reached the final silent stage that awaits them in the distant future. And in the next part of our journey, we will look more closely at those quiet stellar remnants. Because white dwarfs, the glowing embers of ordinary stars, are the beginning of the long road that eventually leads to the mysterious objects known as black dwarfs. When an ordinary star like our Sun reaches the final stages of its life, its transformation does not happen in a single dramatic moment. Instead, the star changes gradually, almost gently, shedding its outer layers and revealing the dense core hidden inside. For a time, the dying star becomes something truly beautiful. As the star expands into a red giant and begins losing its atmosphere, the gas drifting away into space starts to glow. Radiation from the hot stellar core illuminates these expanding clouds, creating delicate shapes and glowing shells that drift outward through the darkness. Astronomers call these glowing clouds planetary nebulae. The name can be confusing because planetary nebulae have nothing to do with planets. The term comes from early astronomers who viewed them through small telescopes and thought the glowing disks resembled distant planets. But in reality, planetary nebulae are the last breaths of aging stars. They are cosmic sculptures made of expanding gas, glowing softly for tens of thousands of years before eventually dispersing into space. If you could watch one of these nebulae from afar, the scene would appear almost peaceful. Layers of glowing gas drift outward like slow waves in a cosmic ocean. Some nebulae form elegant rings. Others appear as glowing bubbles or symmetrical shapes, with delicate filaments of gas spreading outward. Each one is unique, and at the center of every planetary nebula lies the exposed heart of the dying star, the core that once powered the star's fusion reactions. This core is incredibly hot. Temperatures on its surface may exceed 100,000 degrees Celsius, far hotter than the surface of our Sunday. Yet despite this extreme heat, the core is no longer producing energy through nuclear fusion. The fusion reactions that once balanced gravity have stopped. What remains is simply the dense remnant of the star's interior. And this remnant becomes a white dwarf. White dwarfs are among the strangest objects in the universe. They are roughly the size of Earth, yet they contain nearly as much mass as the Sunday. To imagine how dense this is, consider compressing the entire mass of the Sun, over 300,000 times the mass of Earth, into a sphere about the size of our planet. The result is a star remnant with incredible density. A teaspoon of white dwarf material would weigh several tons. The gravity at the surface of a white dwarf is extremely strong. If you could somehow stand on its surface, your weight would increase thousands of times. But in reality, the surface itself is not something a person could ever stand on. The matter inside a white dwarf exists in an unusual state. Unlike normal stars, white dwarfs are not supported by the pressure created by fusion. Instead, they are supported by something called electron degeneracy pressure. This pressure comes from the strange rules of quantum mechanics. Electrons, tiny particles inside atoms, cannot occupy the same quantum state as one another. When matter is compressed to extremely high densities, the electrons begin to resist being squeezed any closer together. This resistance creates a pressure that prevents the star from collapsing further. It is this quantum pressure that holds up the white dwarf against gravity. Without it, the star's core would collapse even further. The balance between gravity and electron degeneracy pressure creates a stable object. A white dwarf is incredibly dense, but it is also stable. It will not collapse unless it somehow gains too much mass. For most white dwarfs, this balance allows them to remain intact for unimaginably long periods of time. But even though the star no longer produces energy through fusion, it still shines. This glow comes from the heat left over from its earlier life. The interior of a newly formed white dwarf is extremely hot, and that heat slowly escapes into space. At first, the white dwarf shines brightly. Over time, it gradually becomes dimmer. Its temperature slowly decreases. But this cooling process happens incredibly slowly. White dwarfs are like cosmic embers. Imagine a piece of metal heated in a furnace until it glows white hot. If you remove the metal and place it in a dark room, it will continue glowing for a while. Gradually, the glow fades. The metal cools. Eventually, it becomes dark again. A white dwarf behaves in a similar way, but on a timescale far beyond anything we experience in everyday life. Instead of cooling over minutes or hours, a white dwarf cools over billions and trillions of years. Even the oldest white dwarfs in our galaxy are still glowing faintly today. The universe itself simply has not existed long enough for them to cool completely. Over time, the planetary nebula surrounding the white dwarf continues expanding. The glowing gas becomes thinner and fainter as it spreads outward. Eventually, the nebula fades away entirely. Its gas mixes with the surrounding interstellar medium, the vast clouds of material drifting between the stars. From those clouds, new stars may eventually form. In this way, the death of one star contributes material to the birth of others. Meanwhile, the white dwarf remains behind, a small, hot, dense remnant drifting quietly through the galaxy. It may orbit the center of the Milky Way for billions of years, slowly cooling, slowly fading. There are likely billions of white dwarfs in our galaxy alone. Many of them are invisible to the naked eye because their light is faint compared to ordinary stars. Yet they represent the final stage of life for the vast majority of stars in the universe, including, one day, our own Sunday. About 5 billion years from now, the Sun will expand into a red giant, shed its outer layers, and leave behind a glowing white dwarf at the center of a planetary nebula. For a time, that white dwarf will shine brightly. Then slowly, quietly, it will cool. And that cooling will continue for an almost unimaginable length of time. Trillions upon trillions of years. Long after the planets that once orbited the Sun are gone. Long after the shape of the galaxy itself has changed. The white dwarf will still remain, a tiny glowing ember in the vast darkness of space. And in the next part of our journey, we will explore what happens during that long cooling process. Because white dwarfs, though quiet and stable, are only halfway along the path that eventually leads to something even stranger. A stage of stellar evolution that belongs not to the present universe, but to a far future age of the cosmos, the silent era of the black dwarf. When a star finishes shedding its outer layers and leaves behind a white dwarf, the dramatic parts of its life are already over. The violent swelling into a red giant has passed. The glowing shells of the planetary nebula have begun drifting away into the galaxy. What remains at the center is something much quieter. A small, dense, glowing remnant. A white dwarf. Unlike the bright stars we see in the night sky, a white dwarf is no longer powered by nuclear fusion. The powerful reactions that once converted hydrogen into helium and later helium into heavier elements have completely stopped. The nuclear furnace that once fueled the star has gone silent, yet the white dwarf still shines. The reason it shines is surprisingly simple. It is still hot. When the star collapsed into its dense final core, enormous amounts of heat remain trapped inside. This heat slowly leaks outward into space. So instead of producing new energy through fusion, the white dwarf glows simply because it is cooling. In this way, a white dwarf behaves like a cosmic ember. Imagine a piece of iron that has been heated in a forge until it glows bright white. When it is removed from the fire, it does not immediately turn cold. It continues to glow. Gradually, the brightness fades as the metal cools. A white dwarf is similar, but on a scale far beyond human experience. At the moment of its birth, a white dwarf can be extremely hot. Surface temperatures may reach 100,000 degrees Celsius, or even more. At these temperatures, the star glows with an intense bluish-white light. But unlike ordinary stars, a white dwarf does not replenish its energy. There is no fusion in its core, no new heat being created, only the slow loss of the heat that already exists. This means that the white dwarf will spend the rest of its existence cooling. At first, the cooling happens relatively quickly. In the early millions of years, the white dwarf radiates large amounts of energy into space. Its temperature gradually drops. Its color slowly shifts. From bright blue-white, the star becomes slightly dimmer and whiter. Later, after hundreds of millions of years, it may appear more yellowish. Eventually, after billions of years, it becomes faint and reddish. This gradual dimming reflects the steady loss of heat. But even though the process is continuous, it is also incredibly slow. White dwarfs cool on timescales that stretch far beyond the lifetimes of most stars. Inside the white dwarf, the matter remains incredibly dense. The atoms are packed together tightly, their electrons forming what physicists call a degenerate gas. This strange state of matter obeys the rules of quantum mechanics rather than the ordinary physics we encounter on Earth. Because of electron degeneracy pressure, the white dwarf remains stable even as it cools. Gravity tries to compress the star further, but the quantum pressure of the electrons resists that compression. As a result, the white dwarf stays almost exactly the same size while it cools. Its structure remains stable for unimaginable lengths of time. Over billions of years, something remarkable begins to happen inside the white dwarf. As the temperature continues to drop, the dense matter inside the star begins to crystallize. This means that the atomic nuclei arrange themselves into an orderly lattice, similar to the structure of a crystal. In some sense, the interior of the white dwarf slowly turns into an enormous cosmic crystal. Astronomers sometimes describe this process as the star freezing from the inside out. The core solidifies first. Gradually, the crystallized region grows outward. Over trillions of years, much of the star's interior may become solid, a gigantic crystalline sphere floating silently through space. Even as this transformation occurs, the white dwarf continues losing heat. The glow becomes dimmer and dimmer. The star that once shone brilliantly as a red giant and later as a hot white dwarf slowly fades toward darkness. Yet the cooling process is incredibly long. The universe itself is currently about 13.8 billion years old, but white dwarfs require trillions of years to cool completely. This means that even the oldest white dwarfs we observe today are still relatively warm compared to their ultimate fate. They still glow faintly. Their light may be dim, but it has not disappeared. In the vast population of stars in our galaxy, white dwarfs are actually very common. Astronomers estimate that billions of them exist within the Milky Way. Some are newly formed and still quite bright. Others are ancient remnants that have been cooling quietly for billions of years. They drift through space like small glowing embers scattered throughout the galaxy. Most are too faint to see with the naked eye, but powerful telescopes can detect their subtle light. Each one represents the quiet afterlife of a star that once burned brightly. And yet, even the oldest white dwarfs we can observe have not reached the final stage of their evolution. They are still cooling, still glowing faintly, still slowly releasing the heat stored during their formation. The transformation into something darker has not yet occurred, because the universe itself is still too young. In fact, the entire history of the cosmos from the birth of the first stars until now has not provided enough time for a white dwarf to cool completely. All the white dwarfs we see today are still somewhere along their long journey toward darkness. In the distant future, that journey will continue. The glow will fade further. The star will become dimmer and colder. Eventually, after unimaginable spans of time, the last traces of heat will escape. And when that moment finally arrives, the white dwarf will undergo its final transformation. It will become something new, something colder, something darker, a silent remnant drifting through a universe where even the faint embers of stars have gone cold. In the next part of our journey, we will explore just how long that cooling process truly takes, because the path from white dwarf to black dwarf unfolds over trillions of years, a span of time so vast that it stretches far beyond the current age of the cosmos itself. Once a star has become a white dwarf, its dramatic life as a shining star is over. There are no more nuclear reactions taking place in its core, no more fusion pushing outward against gravity. What remains is simply a small, dense sphere of matter that is slowly releasing the heat it once contained. From this point forward, the white dwarf begins an extraordinarily long process of cooling. At first glance, cooling might sound simple. Many things cool down after they are heated. A cup of tea left on a table slowly loses its warmth. A metal rod removed from a furnace gradually returns to room temperature. But the cooling of a white dwarf is nothing like these everyday experiences. The amount of heat stored inside a white dwarf is immense. After all, the star was once the blazing core of a sun-sized object. That heat does not disappear quickly. Instead, it leaks into space little by little over periods of time that stretch far beyond the entire history of human civilization. In fact, the cooling of a white dwarf unfolds over trillions of years. To understand just how long that is, it helps to compare it with the age of the universe. The universe itself is about 13.8 billion years old. That number already feels enormous, far beyond any timescale we normally imagine. But 1 trillion years is about 70 times longer than the current age of the universe. And the full cooling process of a white dwarf may take even longer than that. When a white dwarf first forms, it is incredibly hot. Its surface may glow at temperatures above 100,000 degrees Celsius. At this stage, the star shines brightly, emitting strong radiation into space. Over time, however, the white dwarf begins losing energy. Photons, tiny packets of light, carry heat away from the star's surface. Slowly, the temperature begins to drop. The light emitted by the star gradually becomes weaker. During the early stages, the cooling process moves relatively quickly by cosmic standards. Over hundreds of millions of years, the white dwarf may cool from extremely hot temperatures down to something closer to the surface temperature of our Sunday. But as the star grows cooler, the rate of cooling begins to slow. This happens because less energy remains inside the star to escape. The white dwarf becomes like a glowing ember that fades more and more slowly as its heat diminishes. Another remarkable change begins to take place deep within the star. As the temperature drops, the matter inside the white dwarf gradually begins to crystallize. This may sound surprising at first. We normally think of stars as balls of gas or plasma, but inside a white dwarf, the conditions are very different. The intense gravity has already squeezed the atoms so closely together that they form an incredibly dense state of matter. When the temperature becomes low enough, the atomic nuclei settle into an orderly pattern. They arrange themselves into a rigid lattice structure. In other words, the interior of the white dwarf begins turning into a gigantic crystal. This process begins at the center of the star, where the pressure is greatest. Slowly, the crystalline region grows outward as the star continues cooling. Over billions and trillions of years, much of the white dwarf may become solid. Astronomers sometimes describe this as the star slowly freezing from the inside out. Despite these internal changes, the white dwarf's overall structure remains remarkably stable. Unlike ordinary stars, which are supported by thermal pressure created by fusion, a white dwarf is supported by something much stranger. It is held up by electron degeneracy pressure, a quantum mechanical effect that prevents electrons from being squeezed too closely together. Because of this quantum pressure, the star does not collapse as it cools. Instead, it remains roughly the same size, even as its temperature falls. This means the white dwarf can persist for extraordinary lengths of time. Billions of years pass, then trillions. Still, the star remains. Over these vast stretches of time, the brightness of the white dwarf slowly decreases. At first, it may still appear as a faint star, visible through powerful telescopes. Later, it becomes dimmer. Its light shifts toward red wavelengths as the temperature falls. Eventually, the star grows so faint that detecting it becomes extremely difficult. Astronomers studying white dwarfs today can actually estimate their ages by measuring their temperatures. The cooler the white dwarf is, the longer it has been cooling. In this way, white dwarfs act like cosmic clocks, helping scientists estimate the ages of star clusters and regions of the galaxy. But even the coolest white dwarfs known today are still far from reaching their final stage. They are still glowing, still radiating faint heat, still slowly cooling. To reach the next stage, the stage known as a black dwarf, a white dwarf, must cool until it no longer emits visible light at all. It must become completely cold and dark. But the universe simply has not existed long enough for that to happen yet. The oldest white dwarfs we observe today have been cooling for perhaps 10 billion years. That may sound like an unimaginably long time, yet compared to the trillions of years required to create a black dwarf, it is still only the beginning. In fact, the first black dwarfs will not appear until the universe is hundreds or thousands of times older than it is today. This means that black dwarfs belong to a future era of the cosmos, an era that humanity will almost certainly never witness directly. During that distant future, most stars will have already completed their lives. Many will have become white dwarfs. Others will have collapsed into neutron stars or black holes. The bright era of star formation will gradually fade. Galaxies will contain fewer and fewer shining suns. Instead, the universe will become filled with ancient stellar remnants, objects quietly cooling in the darkness. Among those remnants, white dwarfs will be extremely common, each one slowly losing heat, each one moving gradually toward its final state. Eventually, after unimaginable spans of time, the temperature of a white dwarf will drop so low that it no longer glows at all. Its light will vanish completely. What remains will be a cold, dark object drifting through space. A star that has finished its long cooling journey. A remnant so faint that it blends into the darkness of the universe itself. This object is what astronomers call a black dwarf. But for now, that stage still lies far in the future. Every white dwarf we see today is still partway along its long path of cooling, still glowing faintly, still releasing the last traces of heat left over from its former life as a star. In the next part of our journey, we will imagine what happens when that final glow eventually fades away, when the last embers of a white dwarf disappear, and the quiet remnant of a once brilliant star becomes something entirely dark, the mysterious objects known as black dwarfs. For billions of years, a white dwarf drifts quietly through space, glowing faintly with the heat left over from its former life as a star. At first, the glow is still strong enough to be seen across vast distances. Astronomers observing distant star clusters can easily detect young white dwarfs because they remain hot and bright compared to the cold darkness surrounding them. But time in the universe moves slowly and relentlessly. Year after year, million after million, billion after billion, the white dwarf continues its long process of cooling. Unlike a normal star, nothing inside the white dwarf produces new energy. There are no nuclear reactions left to sustain its brightness. Instead, the star slowly releases the heat that was trapped inside when its core first formed. Each photon of light that escapes carries away a tiny piece of that energy. Gradually, almost imperceptibly, the star becomes cooler and dimmer. At first, the change is subtle. A newly formed white dwarf may shine with a brilliant bluish-white light. Its surface temperature can reach tens of thousands of degrees. But as the centuries and millennia pass, the surface temperature slowly declines, from 100,000 degrees to 50,000, from 50,000 to 20,000. Eventually, after many millions of years, the temperature drops closer to that of ordinary stars like the Sunday. But unlike the Sun, the white dwarf is no longer powered by fusion. Its glow is simply the last warmth leaking out into space. Over longer timescales, the change becomes more noticeable. As the temperature falls, the color of the white dwarf shifts. At extremely high temperatures, the star appears bluish-white. Later, it becomes more white or pale yellow. Still later, as the cooling continues, the light begins to take on a reddish tint. This color change reflects the steady loss of heat from the star's surface. The same physical principle can be observed on Earth. A piece of metal heated in a furnace glows white-hot at first. As it cools, the glow turns yellow, then red, and eventually disappears altogether. A white dwarf follows the same basic pattern, but the process unfolds over billions and trillions of years instead of minutes. Meanwhile, deep inside the star, the transformation continues. The crystallization that began earlier spreads further outward through the interior. The dense matter that once behaved like a hot plasma gradually becomes more ordered. Atomic nuclei settle into rigid structures. The star slowly becomes more solid. Astronomers sometimes describe this stage as the formation of a cosmic diamond-like structure because the crystallized interior resembles an enormous lattice of atoms. Yet even as the interior becomes more solid, the surface continues losing heat. The glow grows weaker. The light becomes harder and harder to detect. Eventually, the white dwarf becomes so faint that even powerful telescopes struggle to observe it. From a distance, it no longer appears like a bright star. Instead, it resembles a tiny ember in the vast darkness of space. By this stage, the star may have been cooling for hundreds of billions of years. Civilizations, planets, and entire star systems may have formed and disappeared during that span of time. Yet the white dwarf remains, quietly cooling, quietly fading. As trillions of years pass, the star grows colder still. The surface temperature continues to drop. Eventually, it falls below a few thousand degrees. At this point, the star emits almost no visible light. Most of the energy it radiates lies in the infrared long wavelengths that are invisible to the human eye. To observers in that distant future, the white dwarf would appear almost completely dark. Only sensitive instruments might detect the faint warmth still escaping from its surface. But even that warmth cannot last forever. The cooling process continues. Slow, unstoppable. The last reserves of heat trapped inside the star gradually leak away. Over unimaginable lengths of time, perhaps trillions upon trillions of years, the white dwarf loses nearly all of its thermal energy. The glow that once made it visible finally disappears, and when the star's temperature approaches that of the surrounding universe itself, it no longer shines at all. At that moment, the transformation is complete. The object that once shone as a star, then glowed faintly as a white dwarf, has finally become something new. A black dwarf. A black dwarf is not a dramatic object. It does not explode. It does not emit powerful radiation. It does not shine. Instead, it becomes a silent remnant drifting through space. Cold, dark, invisible against the background of the universe. Its mass remains the same as it was during its white dwarf stage. Its size remains roughly the same as Earth, but its heat and light are gone. The star has become a quiet relic of cosmic history. What makes black dwarfs especially fascinating is that none of them exist yet. The universe simply has not had enough time. Even the oldest white dwarfs we observe today are still glowing faintly. They have been cooling for billions of years, but that is still only the early stages of their long journey. Black dwarfs belong to a future so distant that the universe itself will look very different by then. Galaxies may have drifted far apart. Most stars will have finished their lives. The night sky may contain far fewer sources of light. In that distant era, black dwarfs may quietly populate the cosmos. Small, cold remnants of ancient stars that once shone brightly billions of years earlier. And yet, even though black dwarfs will eventually fill the universe, their story is not only about darkness, because the journey from star to white dwarf to black dwarf reveals something profound about the nature of time in the cosmos. Stars are not eternal, but their remnants can endure for unimaginable spans of time, long after the bright era of star formation has passed. Long after the galaxies themselves have changed, these silent objects will remain, quiet witnesses to the long history of the universe. In the next part of our journey, we will look more closely at what these mysterious objects truly are. Because although black dwarfs have not yet formed, astrophysicists can already describe their properties. And the idea of a completely cold, dark stellar remnant opens a fascinating window into the far future of the cosmos. To understand the idea of a black dwarf, we must imagine a time far beyond the present age of the universe. A time when the stars that currently fill the night sky have long since finished their lives. Most of those stars will eventually leave behind white dwarf small, dense remnants that glow faintly with the heat stored during their formation. For trillions of years, those white dwarfs will slowly cool. Their light will grow dimmer. Their temperature will steadily fall. And eventually, after an unimaginably long period of time, the final trace of heat will disappear. When that moment arrives, the white dwarf will enter its final stage. It will become a black dwarf. A black dwarf is, in many ways, the quietest possible remnant of a star. It produces no light. It radiates almost no heat. It simply drifts through space as a cold, dense sphere of matter. Unlike a black hole, it does not trap light with extreme gravity. Unlike a neutron star, it does not emit pulses of radiation or possess powerful magnetic fields. It is simply a star that has cooled completely. A silent object floating in the darkness of the universe. In terms of size and structure, a black dwarf is almost identical to the white dwarf that came before it. It still contains roughly the mass of a star like the Sunday. It is still about the size of Earth. Its interior remains incredibly dense. but its temperature has dropped so low that it no longer emits visible light. In fact, by the time a white dwarf becomes a black dwarf, its temperature may be only slightly above the temperature of the surrounding universe itself. At that point, the star is effectively invisible. What makes black dwarfs especially fascinating is that none exist yet. This may sound surprising. After all, the universe contains hundreds of billions of galaxies, each filled with billions of stars. Many of those stars have already completed their life cycles. Surely some of their remnants should have cooled by now. But the universe simply has not existed long enough. White dwarfs cool extremely slowly. Even after billions of years, they still retain significant heat. Astronomers estimate that the oldest white dwarfs currently observed have been cooling for about 10 billion years. Yet to become a true black dwarf, the cooling process may require trillions of years. That is 1,000 times longer than the current age of the universe. This means that black dwarfs belong entirely to the future of the cosmos. If a civilization existed trillions of years from now, the night sky they observed would look very different from ours. Many of the bright stars that illuminate our sky today would be gone. Most stars would have already completed their evolution. Instead of shining suns, the universe would contain vast numbers of stellar remnants. White dwarfs, neutron stars, black holes, and eventually black dwarfs. These cold remnants would quietly populate the galaxies. By that time, the galaxies themselves may also look very different. Over immense spans of time, gravitational interactions between stars slowly change the structure of galaxies. Stars may be flung outward into intergalactic space. Others may drift closer toward the galactic center. Gradually, the organized spiral patterns we see today may fade. Galaxies could become more diffuse and scattered. Within those ancient galaxies, black dwarfs may drift silently through the darkness, invisible unless they pass in front of a distant star or interact gravitationally with another object. One fascinating possibility is that black dwarfs may sometimes collide with each other. Because they are extremely dense objects, such collisions could produce unexpected events. In certain theoretical scenarios, two black dwarfs merging together might create enough pressure to trigger new nuclear reactions. This could produce a brief flash of light, a rare event in a universe that has otherwise grown dark. But such events would likely be extremely rare. For the most part, black dwarfs would simply exist quietly, cold remnants of stars that died trillions of years earlier. The concept of black dwarfs reminds us that the universe operates on timescales far beyond human experience. Human history spans only a few thousand years. Civilizations rise and fall within centuries. Even the entire recorded history of our species represents only a tiny moment in cosmic time. Yet the evolution of stars unfolds across billions of years, and the final cooling of white dwarfs extends into trillions of years. Black dwarfs belong to an era so distant that it is almost impossible to imagine. An era when the bright, star-filled universe we know today has grown quiet. And yet, in a way, those distant objects are already part of the universe's future. Every white dwarf we see today is slowly traveling toward that final stage. The process has already begun. It simply requires more time than the universe has yet experienced. One day, far beyond the present era of galaxies and shining stars, the first black dwarfs will appear. They will be the final embers of ancient suns. Small, cold, and silent. In the next part of our journey, we will imagine what the universe might look like during that distant era. Because as more and more stars fade away, the cosmos itself will gradually grow darker, and the night sky, once filled with brilliant stars, may become a much quieter place. If we continue our journey far beyond the present age of the cosmos, we eventually arrive at an era unlike anything we know today. A time when the bright, star-filled sky has grown quiet. a time when new stars are no longer being born. Astronomers sometimes call this distant epoch the era of stellar remnants. To understand how the universe reaches this stage, we must think about how stars form in the first place. Stars are born from vast clouds of gas drifting through galaxies. These clouds, made mostly of hydrogen, collapse under gravity, slowly gathering into dense regions where new stars ignite. For billions of years, this process has been happening across the universe. In spiral galaxies like the Milky Way, glowing regions of gas mark the places where young stars are forming even today. But the gas that fuels star formation is not endless. Each new generation of stars consumes some of that hydrogen. Some gas is also blown away by supernova explosions or carried off by powerful stellar winds. Gradually, the amount of star-forming material inside galaxies begins to decline. Over extremely long timescales, tens of billions of years, the supply of cold hydrogen gas becomes scarce. Without that gas, new stars can no longer form easily. Star formation slows. Eventually, it stops altogether. The universe enters a period where no new stars are being created. Astronomers sometimes refer to this as the end of the stellar era. By this point, most of the bright stars we see today will have already finished their lives. The most massive stars disappear first, exploding as supernovae or collapsing into black holes. Smaller stars live much longer, sometimes for trillions of years. But even these long-lived stars will eventually run out of fuel. And when they do, they too will leave behind remnants. White dwarfs, neutron stars, black holes, and eventually black dwarfs. As the last stars fade, the night sky begins to change. Imagine standing on a planet in that distant future. The familiar constellations would no longer exist. Many of the stars that once formed those patterns would have already died. The bright regions of star formation that once illuminated galaxies would be gone. The sky would appear darker, quieter. Much of the light that once filled the universe would have disappeared. Galaxies themselves would still exist, but their appearance would be very different. Today, galaxies glow with the combined light of billions of stars. In the distant future, however, those stars will gradually vanish. Only faint stellar remnants will remain. White dwarfs slowly cooling. Neutron stars spinning quietly in the darkness. Black holes drifting invisibly through space. And eventually, the cold remnants known as black dwarfs. These objects will dominate the contents of galaxies. Without bright stars, galaxies would become extremely dim. From a distance, they might appear almost invisible. Only faint radiation from stellar remnants and occasional interactions between objects might reveal their presence. In some cases, two stellar remnants might pass close to one another. Gravity could alter their paths, sending them drifting in new directions through space. Over immense spans of time, gravitational encounters like these slowly rearrange the contents of galaxies. Stars and their remnants may be flung outward into intergalactic space. Others may drift toward the center of the galaxy. Eventually, many galaxies may become more diffuse, their contents scattered across enormous distances. Meanwhile, the universe itself continues expanding. The expansion of space gradually carries galaxies farther apart from one another. Over billions and trillions of years, distant galaxies move beyond the reach of visible observation. Even if a civilization existed during this era, it might see only its own local galaxy cluster. All other galaxies would have moved so far away that their light could no longer reach them. The universe would appear smaller, darker, and more isolated. In this future cosmos, the objects that once seemed rare will become the most common. White dwarfs, now cooled and dim, will drift through galaxies as faint stellar relics. Neutron stars will continue their quiet rotations, though many will have slowed significantly over time. Black holes will remain, invisible except for the gravitational influence they exert on nearby objects. And among these remnants, the first black dwarfs will begin to appear. These cold objects will mark the final stage of stellar evolution. They will not shine. They will not emit heat. They will simply exist. Small, dense spheres of matter drifting through the darkness. Despite the fading of starlight, the universe will not be entirely static. Gravitational interactions will continue. Occasionally, two stellar remnants may collide. White dwarfs might merge together, possibly producing brief flashes of energy. Black holes may slowly merge after long orbital dances. Even in a quiet universe, gravity continues shaping the motion of objects. But compared to the bright, energetic universe we know today, these events will be rare. Long periods of silence will separate them. The cosmos will feel calm, almost asleep. It is remarkable to realize that the era we live in now, the age of bright galaxies filled with shining stars, is only one chapter in the much longer history of the universe. In the far future, that chapter will close. The stars will finish their lives. Their remnants will remain, and the cosmos will grow darker. Yet even in that darkness, the universe continues its slow evolution. Stellar remnants drift. Galaxies change shape. Space itself expands ever outward. In the next part of our journey, we will explore what ultimately happens to these stellar remnants. Because even objects like white dwarfs and neutron stars may not last forever. Over unimaginably long spans of time, the matter that makes up these remnants may slowly change, and the universe itself may enter an even quieter and more mysterious era. By the time the universe reaches the era when stars have stopped forming, most of the objects that once filled galaxies with light will have already completed their life cycles. The brilliant stellar furnaces that once illuminated the cosmos will be gone. In their place, the universe will contain the quiet remnants left behind by those ancient stars. These remnants come in several forms: white dwarfs, neutron stars, black holes, and eventually the cold stellar relics known as black dwarfs. Each of these objects represents a different ending for a star, depending on the star's mass and the way its life unfolded. Yet even after their dramatic births, these remnants continue evolving over extremely long periods of time. Their stories do not end when the star dies. In many ways, their longest chapter has only just begun. The most common stellar remnants in the universe are white dwarfs. These objects form when stars similar to our Sun reach the end of their lives. After shedding their outer layers into space as planetary nebulae, the remaining core becomes a small, dense sphere roughly the size of Earth. At first, white dwarfs shine with the heat stored during their formation, but they no longer produce energy through nuclear fusion. They simply cool. Slowly, relentlessly. Over trillions of years, their temperature continues falling. Eventually, their glow fades completely. When this happens, the white dwarf becomes a black dwarf, a cold, dark remnant of a once bright star. White dwarfs are so common that in the distant future, they may make up a large fraction of the visible mass inside galaxies. Yet they are only one part of the story. Some stars end their lives much more dramatically. If a star is several times more massive than our Sun, its core may collapse violently when fusion reactions can no longer support it. The outer layers of the star explode outward in a supernova, and the core compresses into an incredibly dense object known as a neutron star. Neutron stars are among the most extreme objects in the universe. They are only about 20 kilometers across, roughly the size of a city, but they contain more mass than the Sunday. Their density is so great that a teaspoon of neutron star material could weigh billions of tons. Inside these objects, matter exists in forms that cannot be reproduced in any laboratory on Earth. Yet despite their extraordinary density, neutron stars also change over time. Their powerful magnetic fields slowly weaken. Their rapid rotation gradually slows. And like white dwarfs, they eventually cool. Over immense spans of time, neutron stars may become quiet, cold remnants drifting through space. Though they will remain dense and compact, they too will gradually fade into the darkness of the future universe. For the most massive stars, the final outcome is even more extreme. When their cores collapse, gravity becomes so strong that nothing can stop the contraction. The core shrinks beyond the point where even light can escape. The result is a black hole. Black holes are regions of space where gravity has become so intense that an invisible boundary called the event horizon surrounds them. Anything that crosses this boundary cannot escape, not even light. For many years, scientists believed black holes might be completely eternal objects. But modern physics suggests something surprising. According to a theory proposed by physicist Stephen Hawking, black holes may slowly lose energy through a process known as Hawking radiation. This radiation is extremely weak, especially for large black holes. But over vast spans of time, it allows black holes to slowly shrink. The timescale for this process is almost impossible to imagine. A black hole with the mass of the Sun would take roughly 10 to the power of 67 years to evaporate completely. That number is so large that it stretches far beyond even the trillions of years required for white dwarfs to cool into black dwarfs. Supermassive black holes like the ones found at the centers of galaxies would take even longer. Some estimates suggest that these giant black holes could persist for 10 to the power of 100 years or more. Compared to such immense timescales, the entire age of the universe today appears almost insignificant. Yet even black holes are not permanent. Given enough time, they too may fade away. In the far future of the cosmos, galaxies will gradually fill with stellar remnants. White dwarfs cooling toward darkness. Neutron stars drifting silently through space. Black holes slowly evaporating over unimaginable ages. Occasionally, these remnants may interact. Two white dwarfs might collide and merge. Neutron stars may spiral together and produce brief flashes of energy. Black holes might slowly merge into larger ones after long gravitational dances. But such events will become increasingly rare. The distances between objects will grow larger as the universe continues expanding. Encounters will happen less frequently. The cosmos will grow quieter. Among these remnants, black dwarfs may eventually become the most numerous. Every white dwarf that exists today is slowly traveling toward that final state. Given enough time, trillions upon trillions of years, the faint glow of every white dwarf will disappear. What remains will be small, cold spheres of matter drifting through space. The last physical remnants of stars that once shone brightly billions of years earlier. It is fascinating to realize that the bright era of stars, the one we are living in now, is only a temporary phase in the long history of the universe. For billions of years, stars have illuminated galaxies and produced the elements needed for planets and life. But in the distant future, the cosmos will be dominated by objects that no longer shine. Stellar remnants will become the primary inhabitants of galaxies. The universe will gradually transition from a place filled with brilliant stars to a quieter landscape of ancient remnants. And yet, even in this dim future, the story of the universe continues. Gravity still shapes the motion of objects. Space continues expanding. Occasional collisions and mergers still occur, but the overall character of the cosmos changes, from bright and energetic to quiet and slow. In the next part of our journey, we will explore an even deeper question about the fate of the universe, because some theories suggest that matter itself may not last forever. Over extremely long timescales, the particles that make up stars, planets, and even stellar remnants might slowly decay. If that happens, the universe may enter an era even darker than the age of black dwarfs, an age where the very building blocks of matter begin to fade. If we continue imagining the universe far beyond the era of stars, and even beyond the time when black dwarfs begin to appear, we arrive at a future that feels almost impossibly distant. In this future, the cosmos has grown extremely quiet. Most stars have already completed their lives. Galaxies are filled with ancient stellar remnants, drifting slowly through space. White dwarfs, neutron stars, black holes, and eventually black dwarfs. But according to some theories in physics, even these remnants may not last forever. The universe may still have another chapter waiting far beyond the age of black dwarfs. This possibility comes from an idea known as proton decay. To understand proton decay, we first need to think about the particles that make up matter. Everything around us, stars, planets, rocks, oceans, and even our own bodies, is built from atoms. At the center of each atom lies a tiny nucleus made of particles called protons and neutrons. For a long time, scientists believed protons were completely stable. In other words, they would last forever. But some theories in particle physics suggest something different. According to certain models known as grand unified theories, protons might not be perfectly stable. Instead, they could slowly decay into lighter particles. If proton decay exists, it would occur incredibly rarely. A single proton might survive for 10 to the power of 34 years or more before decaying. To put that number into perspective, the universe today is about 10 to the power of 10 years old. So even if proton decay happens, it would occur on timescales trillions of times longer than the current age of the cosmos. For all practical purposes, protons appear perfectly stable in the present universe. But over unimaginable spans of time, the slow decay of protons could gradually change the nature of matter itself. If protons eventually decay, the consequences for the distant future of the universe would be profound. Atoms would slowly break apart. The nuclei that hold matter together would gradually disappear. Materials that seem solid and permanent today, rock, metal, ice, even the remnants of stars would slowly disintegrate. In this distant future, even objects like black dwarfs would not remain unchanged. Because a black dwarf is made of atoms packed closely together, the decay of protons inside those atoms would slowly erode the structure of the star. Over extremely long periods of time, the matter inside the black dwarf would begin to disappear. The star would gradually lose its mass as particles decay and escape into space. The process would be incredibly slow. For trillions upon trillions of years, the black dwarf would remain almost unchanged. But eventually, as more and more protons decay, the dense structure of the star would begin to weaken. The matter that once formed the solid crystalline interior of the black dwarf would slowly dissolve. In the far future, the object might no longer resemble a star at all. Instead, it could become a diffuse cloud of particles drifting through space, a quiet remnant of a star that had once shone billions of years earlier. If proton decay truly occurs, the entire universe would gradually change in a similar way. Matter would slowly dissolve. Stars, planets, and stellar remnants would all eventually break apart. Only extremely stable particles such as electrons, photons, and perhaps neutrinos would remain. The universe would become increasingly empty, increasingly quiet, increasingly simple. This distant period of cosmic history is sometimes called the degenerate era or the dark era of the universe. During this time, the large structures we see today, galaxies filled with stars, would no longer exist in the same form. Instead, the cosmos would be populated mostly by isolated remnants and scattered particles drifting through expanding space. The distances between objects would continue growing as the universe expands. Encounters between objects would become rarer and rarer. The cosmos would feel almost completely still. It is important to remember that proton decay has not yet been observed. Experiments searching for evidence of proton decay have been running for decades, but so far scientists have not detected a single confirmed event. This means that protons may be more stable than some theories predict. Or perhaps proton decay simply occurs on timescales even longer than we have imagined. For now, it remains a fascinating possibility rather than a confirmed fact. Yet the idea of proton decay offers a glimpse into how far the story of the universe may extend. The evolution of stars spans billions of years. The cooling of white dwarfs into black dwarfs may require trillions of years. But the decay of matter itself could unfold over periods that stretch quadrillions or even quintillions of years into the future. Numbers so large that they almost lose their meaning. Yet within those vast stretches of time, the universe continues its slow transformation. When we look up at the night sky today, we see a universe that feels bright and full of life. Stars shine, galaxies glow, nebulae sparkle with newborn suns. But in the deep future of the cosmos, that brightness will fade. The universe will become quieter, darker, more still, and the slow decay of matter may mark the final chapter in the long story of cosmic evolution. In the final part of our journey tonight, we will reflect on what this distant future means for our understanding of the universe. Because even though the cosmos may eventually grow quiet and dark, its story from the birth of stars to the fading of black dwarfs reveals a vast and beautiful cycle unfolding across unimaginable spans of time. If we continue our journey forward through time far beyond the age of stars, far beyond the era when white dwarfs slowly fade into black dwarfs, we eventually arrive at a period of cosmic history that scientists sometimes call the dark era of the universe. This era lies unimaginably far in the future, so far ahead that even the trillions of years required for white dwarfs to cool into black dwarfs represent only the beginning. By this time, the universe will look very different from the one we know today. The bright galaxies that currently fill the cosmos with light will have grown dim. Most stars will have finished their long lives. The familiar glow of stellar light will no longer dominate the night sky. Instead, the universe will be populated mainly by stellar remnants, the quiet remains of ancient stars, white dwarfs that have cooled into black dwarfs, neutron stars drifting silently through space, and black holes that slowly evaporate over immense periods of time. To imagine this era, it helps to picture a galaxy billions or trillions of years in the future. Today, when we look at a galaxy like the Milky Way, we see hundreds of billions of shining stars. Their combined light forms the glowing spiral structure that telescopes capture in beautiful photographs. But in the distant future, that brightness will fade. Star formation will have ended long ago because the gas needed to form new stars will already have been consumed or dispersed. The existing stars will gradually complete their life cycles. Massive stars will explode and vanish quickly. Smaller stars like our Sun will evolve more slowly, eventually becoming white dwarfs. Over trillions of years, those white dwarfs will cool and become black dwarfs. The galaxy will no longer glow with starlight. Instead, it will contain vast numbers of dark stellar remnants. In this future galaxy, the night sky would look profoundly different. Imagine standing on a hypothetical planet orbiting one of the last remaining stars, long before even those final stars fade away. The sky would not contain the rich tapestry of bright constellations we see today. Most of the stars that once filled the sky would already be gone. Instead, the heavens would appear mostly dark. Only faint remnants might occasionally be visible. Perhaps a distant neutron star emitting weak radiation, or a black hole briefly revealed as it interacts gravitationally with another object. But overall, the sky would feel empty. quiet, almost completely dark. Among the most common objects in this era would be black dwarfs. These cold remnants would represent the final stage of stellar evolution for the vast majority of stars that ever existed. Each black dwarf would be roughly the size of Earth. Each would contain the mass of a star like the Sunday, yet they would emit almost no light or heat. To any distant observer, they would be nearly impossible to detect. They would drift silently through the galaxy, invisible against the dark background of space. Over time, countless black dwarfs would populate the universe. They would become the dominant remnants of the once bright stellar population. Yet even in this dark era, the universe would not be completely still. Gravity would continue shaping the motion of objects. Black dwarfs might occasionally pass close to one another. Neutron stars could still orbit each other for billions of years before merging. Black holes might slowly draw in nearby remnants through gravitational interactions. In rare cases, collisions between stellar remnants might produce brief flashes of light, short-lived events in an otherwise dark universe. But such events would be extremely uncommon. The distances between objects would grow larger as the universe continued expanding. Encounters between remnants would become increasingly rare. The cosmos would feel vast and empty. Meanwhile, the expansion of the universe would continue. Over immense stretches of time, galaxies would drift farther and farther apart. Eventually, observers in any single galaxy would no longer be able to see other galaxies at all. The light from distant galaxies would have traveled so far through expanding space that it would never reach them. Each galaxy or cluster of remnants would appear isolated in an enormous cosmic void. The observable universe would seem smaller and lonelier than it does today. Black holes, which may still exist during this era, would also slowly change. According to modern physics, black holes emit tiny amounts of radiation known as Hawking radiation. This process is incredibly slow, but over extremely long periods of time it causes black holes to gradually lose mass. Eventually, even the largest black holes may evaporate completely. When that happens, another source of energy in the universe disappears, leaving behind an even quieter cosmos. At this stage in cosmic history, the universe may contain mostly low-energy particles drifting through expanding space. Electrons, photons, neutrinos, perhaps a few remaining stellar remnants slowly interacting through gravity. But compared to the vibrant, star-filled universe we inhabit today, the future cosmos would be remarkably calm, almost motionless, almost silent. And yet, even this dark future tells a story about the incredible scale of cosmic time. The stars we see tonight represent only one chapter in the universe's history. They were born from clouds of gas billions of years ago. They will shine for billions more. Then they will fade into white dwarfs, neutron stars, and black holes. Eventually, white dwarfs will cool into black dwarfs, and the universe will slowly enter its quietest era. It is fascinating to realize that the bright era of stars, the one we are fortunate enough to witness today, is temporary. We live during a time when galaxies still glow, when stars still form, when the universe still shines. In the far future, that light will fade, but the remnants of those stars will remain, silent witnesses to the long history of the cosmos. And so the story of black dwarfs is not only about the death of stars, it is also about the long journey of the universe itself, from a hot, bright beginning to a distant future where the last lights slowly disappear, a universe that gradually grows quieter, darker, and more still. In the final moments of our journey tonight, we will pause and reflect on what these distant futures mean. Because even though black dwarfs belong to a universe trillions of years away, their story reminds us of the vast and peaceful rhythm that shapes the cosmos itself. And now, as our quiet journey through the distant future of the universe comes to an end, it is worth pausing for a moment to reflect on the story we have explored tonight. The universe is a place of cycles. Stars are born within great clouds of gas drifting through galaxies. Gravity slowly gathers that gas together until the pressure and heat become strong enough to ignite nuclear fusion. A new star begins to shine. For millions or billions of years, that star radiates light and warmth into the surrounding cosmos. It illuminates planets, shapes the chemistry of space, and quietly transforms hydrogen into heavier elements. But no star shines forever. Eventually, the fuel in its core begins to run out. The balance between gravity and fusion changes. The star evolves, grows older, and finally reaches the end of its luminous life. Some stars explode in brilliant supernovae. Others collapse into neutron stars or black holes. And many, perhaps most, end their lives as small, dense remnants known as white dwarfs. These white dwarfs glow softly with the heat left over from their former lives as stars. They shine like cosmic embers, slowly releasing their energy into space. But even that faint glow cannot last forever. Over unimaginable spans of time, trillions upon trillions of years, white dwarfs continue cooling. Their light fades, their temperature slowly falls, and eventually, far beyond the present age of the universe, they become something even quieter, something darker. They become black dwarfs, cold, silent remnants drifting through the vast darkness of space. These objects represent the final stage in the life of stars like our Sunday. They no longer shine. They no longer radiate heat. They simply remain tiny spheres of dense matter floating through a universe that has grown calm and dim. In that distant era of cosmic history, the bright galaxies we see today will have faded. Star formation will have ended, and the universe itself will feel quieter than ever before. Yet even in that silence, the story of the cosmos continues. Gravity still shapes the motion of objects. Space itself continues expanding, and the remnants of ancient stars drift slowly through the darkness. The universe does not end suddenly. Instead, it slowly settles into stillness, almost as if the cosmos itself were drifting towards sleep. So tonight, as you begin to relax and close your eyes, you might imagine that distant future universe. A sky no longer filled with bright stars, but a quiet, peaceful cosmos where ancient stellar remnants float silently through space. Black dwarfs, the final echoes of stars that once shone brightly billions of years earlier. The last embers of the universe. Thank you for joining this calm exploration of one of the most distant futures science can imagine. Wherever you are in the world tonight, I hope this journey through the quiet story of stars has helped your thoughts slow down and settle. Now it's time to rest. Take a slow breath. Let your mind drift gently, and imagine the vast universe stretching peacefully into the distance. Good night. Sleep well. And as the ambient music begins to play softly, allow its gentle sound to carry you into a calm and restful sleep among the quiet stars.